In my last video, I explained how balanced audio actually works. It's impedance, 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 impedance. I actually probably should have said balanced impedance from the very beginning, because that's what they should call it. Totally true. I don't like intro videos. Yeah. So before I begin, there's something that I cut out of my last video that I really wish I hadn't. So thanks to Simon Lewis on the Facebook group Live Sound Engineers for pointing this one out. So if you remember, I talked about defensive noise reduction measures, but the one I left out is pretty critical, and it's called Twistedpair wiring. Basically, all it means is we just take our two wires that we had here, or for instance, these two wires that we have here, and we just twist them together. It's nothing more complicated than that. By doing this twist, I think you can see pretty clearly that now neither wire is closer to any other direction, so noise will hit the two wires at the same level, and basically the two wires will end up with the same amount of noise on them, and when they get to our differential amplifier, the differential amplifier will cancel them out. And that's the whole point. Special thanks to our Cat 5 cable for giving up its life so you could see that. So there are basically two different types of devices used to create balanced circuits. There's transformers, and then there's active balancing circuits. First, let's take a minute to talk about transformers. Transformers have been used since the beginning days of audio circuits and are essentially really simple devices. On the input side, you have a coil of wire wrapped around a center, or what we call a core. So there's our input side of our transformer. On the other side, we have essentially the same thing. We have a coil of wire on another core. And so that's the basis of what a transformer is. So what happens is when you have alternating current placed on this wire, essentially you've got a push-pull of current going back and forth. This induces a magnetic field, and the magnetic field is seen by this coil, which turns around and turns that magnetic field right back into an alternating current of push-pull signal. Because it's alternating back and forth, you can see that when it's pushing this way, of course it's pulling this way, and when it's pushing this way, of course it's pulling this way. So that basically means that you end up with a signal that is equal but in opposite polarity to each other. And that's how a transformer can generate a balanced signal. Now, of course, I've emphasized over and over again that it's critical that these two wires be the same impedance so that they end up with the same amount of noise on them. Well, the neat thing about the transformer is, think about this for a second, these are all the same wire. So of course it has the same impedance because it's literally the same piece of wire. So long as we keep each one of these ends the same length, we're going to end up with an impedance matched load, and consequently we'll end up with the noise canceling that we're looking for. So that's what a transformer looks like when I draw it, which is not great, but you get the idea. There's another way to generate a balanced output, and that's with an active circuit. So what you end up with is something that looks a little bit like this. So inside of this, we end up with some little transistors and maybe a resistor or two, and maybe some pixie dust. Yeah, I don't really understand how electronics work. But as you can see, you end up with essentially the same output. That's just a way for an active circuit to do what a transformer can do. Okay, so clearly I can't draw. This is a perfect representation of a passive, symmetrical, balanced circuit. Basically, these two little things are just little squigglies that are transformers. And so this is basically a transformer balanced circuit. So you can see, even though we have our noise on our two lines, since they're both in the same impedance, of course, they're being canceled out on the output side here. You can see here's our signal, just like I pictured before. You can see that it is exactly out of polarity with itself. And so consequently, this transformer is going to see only the difference and not the things that are the same. And it's going to output a larger version of that wave. Larger because given that this is exactly out of polarity with each other, you can see that the distances between these waves are larger than if it were only on one leg of this circuit. So this is our classic passive symmetrical transformer circuit. Here's a little representation of an active symmetrical circuit. Essentially, all that's happened here is we've replaced our transformers with active circuitry. But essentially what we've got is the exact same thing as we had with our transformers, just with an active circuit. This used to be something that was a lot harder to do. Modern electronics have made this very simple, and in fact, modern active balanced circuits are the most common thing that you see out in the field. Finally, let's talk a little bit about active asymmetrical circuit. This is the circuit that I emphasized so much in my last video, only because many of the circuits that we use out in the field are actually wired this way. And a lot of us just were never aware of it. So you can see on the input side, we've got a signal generator happening on one line, but on this other line, all we've got is a little resistor circuit that's going to ground, that's making sure that this wire and this wire have the same impedance. Lo and behold, our noise happens on both of our wires, and it ends up reaching our distribution amplifier at exactly the same level. And we only have signal put on one wire. That, of course, gives us the same output coming out of the circuit with none of the noise. Now, one of the things you may have noticed is that this signal has twice the amplitude of the signals that we showed on the symmetrical circuits. And that's necessary in order to ensure that our, boy, did I draw that poorly. Anyway, to ensure that the signal level coming out of this type of a circuit is at the same amplitude as the signal wire, as the signal that's going to come out of a symmetrical circuit. So those are the three primary ways that balanced audio is both generated and received, outputs and input side. The beautiful thing is that these can all be used interchangeably. I'm going to show you a little bit of that through the magic of 3D animation. So here we have an active symmetrical output feeding a transformer from a passive symmetrical input and generating exactly what we'd expect it to generate. And here we have an active asymmetrical output feeding an active symmetrical input, basically an active differential amplifier, and outputting the same output. And finally, here's a passive symmetrical output, basically a transformer, feeding an active symmetrical input, basically an active differential amplifier, and you can see this signal is going to spit out exactly the same as if this were an active output. So these things are brilliant and they all work great. And I've got a bunch of pieces of paper. Okay, with so many different options, the next obvious question is, which one is the best? Well, of course, as with all such things, it depends. I mean, transformers are great. They have an advantage of not needing external power. They also can isolate devices physically from each other, which can be very helpful in reducing the chances of ground loops and other issues. But being passive devices, it's difficult to make transformers that can perform well over a wide range of signal levels without introducing some form of distortion. And that means good transformers are expensive. I see you, Jensen. An active symmetrical circuit offers a lot of the same advantages as a transformer and are much cheaper to make. But of course they require a source of power, and they're still more expensive to make than our good friend the active asymmetrical output that I spoke of so lovingly in my entire last video. Asymmetrical active outputs also have an advantage when they're interfaced with unbalanced circuits, but I'm not going to get into that right now. That's all part of my next video, so stay tuned for that. So that's it for now. Stay tuned for my next video where I'm going to talk about all the actual audio connectors that these magic circuits plug into and how all these connectors are basically really stupid. In the meantime, as usual, I've hidden several small errors in this video, so have fun finding those and please let me know when you do. If you like it, hit the like button. If you don't like it, please subscribe. And if you hate it, share it. Thanks so much. See you next time.